Welcome to this lecture on digital elevation models. So what is a digital elevation model, or DEM? This is a broad category, sometimes a little misused, but generally speaking what we're talking about is one of these three main categories. We have a digital surface model. This is the highest point that is measured. This could be rooftops, treetops, as well as the ground. So this is the things that exist both on the surface of the Earth and are built onto the surface of the Earth or growing from it, which can be quite useful for some types of work, but not always. A lot of the time you actually want the ground as it is rather than the things that are on the ground. The digital elevation model, this catch-all term, is strictly speaking it should be the elevation of the ground. What's the thing that you stand on, not any construction on top of it or anything growing on top of it. This is somewhat tricky when considering, say, erratics, things like this, large natural features that exist on the ground but maybe don't affect things like surface runoff directly if you're modeling hydrology, for example. So this could be a problem. You would need to do some filtering of the data and double checking to see whether the person who supplied you with the data or the agency that supplied you with the data has considered such features as being part of the surface elevation, or whether they are part of a digital surface model, this upper layer. And then we have the DTM, the digital terrain model, which sometimes refers to the DEM, but it can also mean things like derived products, topographical products, slope and aspect and what have you. It can also sometimes mean the DSM as well. So there is a lot of misuse of these terms, so be careful, double check what is actually being referred to, should be made clear in the metadata. So just to quickly illustrate the difference between the DEM and the DSM, this is the same area. We can see here that all the buildings that are visible in this digital surface model have been removed from here, and we just interpolate straight over from the sides of the buildings so that we have the ground surface. Now, of course, there could be errors with this. We have no idea what's happening below ground. There could be basements here, things like this. So there are always limitations, especially in these built environments. But this is generally what we're looking at. This will be the difference between the surface with nothing on it, and this is the surface with buildings on it. So that's the DEM, digital elevation model, and the digital surface model. But more generally, what are we talking about? Well, the DEM in all of its forms is a continuous surface. We have information about elevation at all points where our model exists. But each data point, which is not the same thing as the surface itself, but each data point that has been measured is actually a collection of data. It's a statistical measure, as it says here, of a particular area, the support. We have an instrument that is making a measurement, or perhaps several instruments that are making measurements over a particular area, and they require a certain area over which they can gather data from. Commonly we equate this with the ground sampling distance, which is not the same thing as resolution. We've spoken about this before. But the ground sampling distance should then give us our cell size, the area covered on the ground within a raster of a raster cell, and they should be equivalent. The ground sampling distance, the cell size, should be approximately the same as the support, the area required by the measuring instrument to actually gather enough information to make that measurement. And it's important that these cells are not smaller than the support, because then this is like the case of upsampling that we have discussed previously, whereby we can end up with some curious and incorrect interpretations of the data. Above all, things like slope becoming too steeper than they actually are. We also have vector models. Above all, triangulated irregular networks can be used to represent DEMs. And as we don't have this direct connection between the cell size with its ground sampling distance and the support, we just have a point of data, and its representation can have very high precision, well beyond the support. We need to find out what the support is from the metadata, because the characteristics of the spatial data, the geospatial data within the tin itself, don't tell us anything about that support. So this is a silly illustration just showing us the difference in the support size. Generally speaking, the closer we are to the ground, the smaller the area we're gathering data from which to make a measurement. Satellite-based, this is a satellite in case you didn't realize, will, generally speaking, have a larger footprint, a larger support from which it gathers data. So let's look at different methods now. In that previous illustration, we had a satellite and an aeroplane, but they're not our only sources. Especially when working with older data, we might have a DEM derived from a map, a paper map. This is not uncommon, especially within certain fields. For example, in my own field, glaciology, where older surveys of glaciers are stored in paper maps. And if we want to do a comparison, size comparison, we need to redigitize or digitize those DEMs from paper maps. There are, unfortunately, many error sources that we have to consider. For a start, the original survey, we don't know how that was performed in many cases, how accurately that was done. It may have been constructed from different types of surveys as well. Once we actually have the data recorded, or the original surveyors had the data recorded, they then had to draw contour lines to create the map. And these are generalizations. So we are losing some information there as well. We're also gaining some in many respects. Traditional contour lines were drawn using expert knowledge. So perhaps we have an enrichment of the information, but maybe not. So this is always very difficult. It's very, very tricky. But then in the process of digitizing those paper maps, those old paper maps, we've dug them out of a cupboard somewhere, and we're now going to digitize them. Well, we have things like the line thickness, so we can't place our lines, these contour lines that we are digitizing, with any greater accuracy than the thickness of the line. We're assuming it's going to be in the middle of the line, and we have to place our new digitized line with its super high precision in the middle if we think that's correct. The printing process itself can smudge lines. Then once we have our lines, in order to create this continuous surface, we need to interpolate between these contours. That in itself is going to introduce new problems. And one of these problems typically is the lack of local extrema, as in high points and low points. The contour lines will go down to a particular level, and unless we actually have a specific point, elevation point sat within in a topographical low point or at a top, we won't know how far the top reaches. Presumably not as far as the next contour line, but how far from it, we don't know. And these local extrema tend only to exist at the highest points within a region. On what scale it will vary depending on the original cartographer, rather than these local small-scale tops or